In this video, we will discuss Lewis structures, Vesper, and formal charge and what makes something the best Lewis structure. So I'm going to go through the Lewis structure rules kind of quickly because we're going to just practice with them. Make sure you have the correct number of valence electrons in your compound. You're going to connect everything together with a bond, and typically the unique atom is going to be your central atom. We're going to talk about why it's not too bad to figure out the central atom on the AP test. You're going to make sure you remember that hydrogen is never going to be your central atom, so it's always going to be a terminal atom. And we're going to add lone pairs to make sure that each element has 8 electrons, but of course hydrogen, because it's in the first energy level, it could have a maximum of 2 electrons, so it does not get 8 electrons. And just some things that sometimes show up is that boron and aluminum typically only form 3 bonds, whereas beryllium typically forms 2 bonds. And you don't want to forget an octet around your central atom. Now, if your electron count is too many, then what you're going to do is you're going to remove 2 lone pairs from you're going to remove 2 lone pairs total. 1 lone pair from your central atom and 1 lone pair from a terminal atom. And then you're going to add a multiple bond in between those atoms, and you're going to do this until your count matches the correct number of valence electrons for each compound. Now, if your count is too few, so you've given everything 8 electrons and your count is still too few, then you just add a pair of electrons to your central atom. So if you're 2 short, then you just add it to your central atom. But if you are 4 short, then you just add 4 electrons or 2 pairs to your central atom. This will only happen when your central atom can exceed an octet, and that only happens when your central element is in the 3rd row or lower on the periodic table, meaning that they have access to d orbitals. Now, formal charge. Formal charge you technically only need to do if your central element has access to d orbitals. So, what I mean by that is everything has a formal charge. You can figure out the formal charge for everything. And the way that I do Lewis structures is that the formal charge for elements that are in the 2nd row on the periodic table, you can't end up changing them because if you remember, we've already given them 8 valence electrons. And so because the 2nd row on the periodic table could be a maximum of 2s2, 2p6, which is 8 valence electrons, we can't give those elements any more electrons. So when we do formal charge, though, what we're going to do, this is the way that I do it, we divide each bond in half, count the number of electrons each have with the bonds divided in 2, and then compare that to the valence electrons that the atom typically has. And we're going to see how this works, but all formal charges must equal the total charge of the compound. And then the best Lewis structure is going to be one that minimizes formal charge. Okay, so we're going to see that in a couple examples later on. But first, let's go through. We're going to do our valence count. So chlorine has 7 valence electrons, oxygen has 6, and so if I add this up, I get 32 valence electrons, and my central element is going to be chlorine. I'm going to bond oxygen around here. Then I'm going to give everything 8 valence electrons. And then I'm going to count. And when I count, I say I've got 2, 4, 6. I like to count in pairs, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I do have 32, so my count is good. A lot of people would say, well, this must be the Lewis structure, and I say, okay, well, maybe, but we've got to consider formal charge. So because chlorine, our central element, occurs in the 3rd row on the periodic table, that means we really do need to go through and do formal charge because the formal charge could change the Lewis structure. So what I'm going to do is I'm going to divide each of my bonds in half, and then I'm going to count the valence electrons that each of them have, with the bonds divided in half. So oxygen normally has 6 valence electrons, according to the periodic table, but here, what I can count is I see 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is -1. So these oxygens have a -1 formal charge. Okay, now let's go ahead and do the same for chlorine. Chlorine, according to the periodic table, normally has 7 valence electrons, and right now it has 1, 2, 3, 4, with the bonds divided in half, and so 7 minus 4 would be a positive 3 formal charge, so chlorine here has a positive 3 formal charge. And so then I have to ask, do I have an attraction going on? Is there a negative attracted to a positive? And the answer is yes. I have these negative oxygens right next to a positive chlorine. So what you're going to do is you're going to pick one of the oxygens, you're going to erase a pair, but you're not going to permanently erase a pair. What we're going to do is we're going to create a multiple bond. We're basically just moving those electrons in to form a multiple bond, and now the formal charge is going to change. And so oxygen, I count 1, 2, 3, 4, 5, 6. Oxygen normally has 6, so that's a formal charge of 0. And chlorine right now has 1, 2, 3, 4, 5. Chlorine normally has 7. 7 minus 5 would be a positive 2. And so chlorine's formal charge is getting minimized because we're getting closer to 0. So then I got to ask myself the same question. Is there an attraction going on? And the answer is yes, and that's because there is a positive right next to a negative, and I could pick any of the oxygens. So I'm going to do the same process. I'm going to erase a pair, and then I'm going to form a multiple bond. And what that does is that changes this oxygen to a formal charge of 0. This chlorine goes down to a formal charge of +1. And so then I have to ask myself the question is there still an attraction going on, a positive sitting next to a negative? And the answer is yes. So I'm just going to pick the top oxygen. I could have picked the bottom oxygen as well. There is a negative next to a positive, so what I'm going to do is I'm going to erase a pair of electrons, but I'm not permanently erasing them. I'm just moving them into the bonding area. What that does for me is this chlorine now goes to 0, this oxygen now goes to 0, and so my formal charge has been minimized. I still got charge, but I know that I'm done because I ask myself the question, and I say, is there a negative sitting next to a positive, being directly adjacent to a positive? And the answer is no, because chlorine is now 0. So there's no longer an attraction going on. And so what I'm going to do is I'm going to just clean this up for you. And this is what our Lewis structure will look like. We'll have 3 double bonds and 1 single bond. And the reason why this is our best Lewis structure is that we've minimized the formal charge, meaning that we have the most minimal amount of charge going on. And I'll form a bracket just to say that it's overall a -1 formal charge. And also, some people get confused with what resonance means. Resonance, as far as AP chemistry is concerned, resonance means where I have double bonds and single bonds, and I technically could have put the double bond, let's say, down here. And so because I picked here to put the double bond, those 3 places, this has resonance where the Lewis structure, let me try to get this copied, the Lewis structure could have looked like this, where the double bond is there, and then the single bond is there. So that's one Lewis structure. The Lewis structure could have looked like this, where the single bond is up at the top. Or the Lewis structure could have looked like this, where the single bond is off to the right. And so what that means is that this does have resonance because there were multiple places where I could have put the single bond. or the double bond, whatever you want to think about it like. Okay, so that is our Lewis structure. We're going to do ClO3, so that would be 7 and 6. 6 times 3 is 18, plus 1 plus 7 would be 26. Our central atom will be chlorine. We'll go ahead and bond all of our oxygens here. Give everything 8 valence electrons. And what a lot of students do is they will forget to put 8 valence electrons on your central element. So then I'm going to go through and I'm going to count. I'm going to say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So my valence count is good. But what I want to do is I want to go through and I want to do formal charge. I've got to do formal charge because chlorine occurs in the third energy level, meaning that if I needed to minimize the formal charge, chlorine does have d orbitals that could accept those electrons. So when I go through and do this, oxygens, all of these guys have a -1 formal charge. Chlorine has 1, 2, 3, 4, 5, so that would be a +2 formal charge. And as you get reviewing with this, you're going to come to realize that because I have +2 and all these -1s, that means that I'm going to basically form 2 double bonds, so I could pick any oxygens to do that with. And I'm going to erase those electrons, but I'm not permanently erasing them. I'm just moving them and creating a bond. So what that does is these formal charges change, and this becomes 0, 0, 0. And so my total formal charge adds up to B -1, which is the charge of ClO3. And so this is my Lewis structure. It's the best Lewis structure because I minimize the amount of charge that goes on. And so yes, this does have resonance. Okay, let's do ClO2. 7 plus 12 plus 1. We've got 20. Our central element will be Cl. We'll bond oxygen to there, give everything 8 valence electrons. And when I've given everything 8 valence electrons, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that works out. We will come across an example later in this video where we'll have to do other things where the count doesn't check out. But now what I want to do is I want to figure out the formal charge. And when I do formal charge, this is -1, this is 1, 2, 3, 4, 5, 6, this is +1, this is -1. So yes, I can create a multiple bond. I will erase a pair of electrons, form a multiple bond. What that does is that changes this to 0, this to 0, and that to -1. That one stays. And so this is my Lewis structure. It minimizes our formal charge, and because I put the double bond on the left, but I could have chosen the right, this does have resonance. Okay, now let's jump around for some examples. Like let's do SO3 versus SO3 -2. So SO3 is going to have a valence count of 24. SO3 2- is going to have a valence count of 26. I'm going to bond all of my oxygens to my sulfurs. I'm going to give everything 8 valence electrons, and then I'm going to do each of them individually just to see how they're kind of different. Okay, so I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that means I've got too many valence electrons, and we haven't seen an example like that just yet in this video. So I need to get down to 24. So what happens when you have too many is you erase a pair from your central element, and then you pick any of your terminal elements and you erase a pair. And then you create a multiple bond between them. So now I do have 24. I can just confirm that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that sounds good. And then I've got to ask myself the question, I have the right valence count, but do I have to do formal charge? And the answer is yes. Okay, sulfur occurs in the third energy level, so I'm going to slice all my bonds in half, and when I do that, sulfur is going to have a +2 formal charge, the single bonded oxygens will be -1, and the top oxygen will be 0. So you got to ask yourself the question, do you have an attraction going on, meaning do you have a positive sitting right next to a negative? And the answer is yes. So I'm going to erase a pair there, form a multiple bond. That brings this oxygen's formal charge down to 0. Sulfur goes down to +1. I'm going to do the same. I'm going to erase a pair and move those into the bonding area. That moves this formal charge to 0 and sulfur down to 0. And so this is the best Lewis structure because it completely minimizes a formal charge, meaning there's no charge going on. Now, let's look at SO3 2-. For SO3 2-, what we have going on is I need 26 valence electrons. So let me just count and see where I'm at. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I do have 26 valence electrons, so I don't have to worry about anything right now in terms of my valence count, but I do need to consider my formal charge. And with formal charge, when I slice all my bonds in half, all the oxygens, they are -1, and my sulfur is going to be +1, and so I do have an attraction going on. I'm going to pick any of my oxygens. I'm just going to pick the right one, and I'm going to move those electrons to create a multiple bond. That brings the oxygen formal charge down to 0, and then the sulfur formal charge down to 0. I no longer have an attraction, so I am done. So let's answer the question about resonance. We picked this right oxygen to create the multiple bond. So what that means is I could have picked any of the other oxygens. So because of that, yes, this has resonance. If I wanted to draw the resonance structures, I would strictly just draw this same structure, but the double bond might be there, or it could be there, and then the rest would be single bonds. For my SO3 here, I would say no resonance because I never really had a choice of where I put the double bonds. Okay, so a clue that you'll have resonance is when you have double bonds and single bonds and you had a choice where you put your double bonds. Okay, and then to just finalize this, I'll put a bracket around it and call it a -2 charge. Okay, let's look at some weird ones, and then we'll call it quits on some of these. Let's look at Br3 with a -1 charge. So with Br3 with a -1 charge, that valence count will be 7 times 3 plus 1, so 22. And a lot of students will try and they'll say, oh, I'm going to bond it into a triangle. Okay, and I always say, do not make an Illuminati triangle. That is not going to be good for a Lewis structure. Very unstable. If you take organic chemistry, you'll learn that the bond string or the ring strain there would just be too high that it's not likely to happen. So what you should do is just bond them into a line. Go ahead, give everything 8 valence electrons. And when I've done that, I'm going to go through and count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And so I need 2 more. So the rule of when you need more is you just add them to your central element. And so there we go. I do need to go ahead and do formal charge because bromine is in the 4th energy level, meaning it has access to d orbitals that it could expand its octet, which we've already seen because this central bromine definitely exceeds an octet. But that is okay. So when I go through and do formal charge, I have 0 for bromine, -1, and 0. And so I can't change anything because there's not an attraction. There's not a negative sitting next to a positive. So I just put my bracket on it and call it a day. Okay, let's look at something like carbon monoxide. Its valence count will be 10. We don't have a central element, and by the way, whenever you have just 2 elements bonded together, its shape will always be linear. Okay, so carbon would be bonded to oxygen. Go ahead and give everything 8 valence electrons. And when we do, we go ahead and we say, okay, I've got 2, 4, 6, 8, 10, 12, 14, so I need to get rid of that. When you need to lower your count, you erase a pair from your central element and one of its terminal elements. Here, we don't really have a central element, so we just erase a pair from each of them, create a multiple bond, then we count again, and when we count, we've got 2, 4, 6, 8, 10, 12. Okay, we need to get down to 10, so we'll do that process one more time to get down to 10, and you can pick any lone pairs. They don't have to be perfectly the same one. And so now I have carbon monoxide, and then I've got to ask myself the question, should I do formal charge? And the answer is I can, but it's not going to change anything. So because carbon and oxygen already have 8 valence electrons, they cannot exceed an octet because the second energy level does not have access to d orbitals. There are no 2d orbitals. But I'll go ahead and do formal charge. I'll slice my bonds in half, and I will say, okay, carbon has a -1 formal charge. Oxygen actually has a +1 formal charge. So there is an attraction going on, but we can't do anything about it. That's why it's important to remember if it's in the third energy level or lower. And when I say or lower, I mean in the third energy level, fourth energy level, fifth energy level, lower on the periodic table, you can do something about it, but never if it's in the second energy level. And this partly explains why carbon monoxide is an unstable molecule and why carbon monoxide poisoning is so dangerous. It's because if you breathe in carbon monoxide, it wants to get rid of this formal charge. This molecule is not very stable with that formal charge, and what it does is it bonds to the hemoglobin in your blood and gets rid of this unstable formal charge, and it messes with your hemoglobin. Okay, let's look at O3 ozone. That has a valence count of 18. Bond all of your oxygens together and then give each of them 8. And with that, we've got a count, and I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I need to get down to 18, so when I do that, what I'm going to do is I erase a pair, form a multiple bond, and now I'm down to 18. Do I need to do formal charge? The answer is no, because oxygen couldn't change even if you did do formal charge, because we've already given all the oxygens 8 electrons. But when you do formal charge, you do see that you do have an unstable formal charge situation going on, but you can't change it. Okay, let's do ammonia here. This has a valence count of 8. And this one I just want to do quickly because I want to remind you that we give everything 8 valence electrons except hydrogen. So this is actually our Lewis structure. Okay, now let's go ahead and do hybridization and geometry or the molecular shape. So let's go back to one of these up at the top. And here's what you want to do is you want to figure out how many atoms are bonded to your central element and how many lone pairs your central element has. It's not the number of bonds, but the number of atoms bonded. And that is called the steric number. So if I look at ClO4 here, this chlorine, my central element, has 1, 2, 3, 4 atoms bonded, 0 lone pairs. So it's important to know my Vesper chart, which is right here. So if I have 0 lone pairs and 4 things bonded to it, it is going to be a tetrahedral shape. Okay, so that shape is going to be tetrahedral. And because my steric number is 4, I want to think about my hybridization, and I'm going to write that in red over to the right here. There's only one s orbital in any one energy level. There's only 3 p orbitals in any one energy level. There's only 5 d orbitals in any one energy level, and then we're not going to see f orbitals, but there's 7 f orbitals in any energy level that has f orbitals. So what I want to do is, because we said my steric number is 4, I need my hybridization number to add up to 4. So I could have a maximum of S1, and then p, if I do 3 p's, that would have my exponents add up to be my steric number of 4, so that looks good. Now, let's look at my next one. 1, 2, 3 elements bonded to central chlorine, and then 1 lone pair, so my hybridization needs to be 4 because my steric number is 4, so I get sp3. But my geometry is going to change. A lone pair takes up more space than bonds, and so what happens is we just have to know our shapes, that this is going to be 1 lone pair, still a steric number of 4, and that's going to be trigonal pyramidal. Okay. Okay, and then on here, my steric number is still 1, 2, 3, 4, so it's still sp3, but this is going to be a bent structure. Okay, so you need to know your molecular geometries. If we go to something that looks like this, we have a steric number of 1, 2, 3, 4, 5, so now I need my hybridization to add up to 5. S could be a maximum of 1, P could be a maximum of 3. Right now that only gives me 4, and so D needs to be 1 to get up to 5. That should make sense because remember when we did this Lewis structure, we said bromine is exceeding an octet, and it can do that because it has access to d orbitals. Well, there are the d orbitals. Okay, now your hybridization, if you have something like this of carbon monoxide where we don't have a central element, we're going to see later that you just look at the element, you'd have to do one for carbon and one for oxygen. Carbon is bonded to one other element and it has one lone pair, and so its hybridization is sp because that adds up to its steric number of 2, and oxygen happens to be the same thing. Notice that I'm not counting how many bonds, but I'm counting the number of atoms bonded. Okay, so let's just go over some general bond properties that show up a lot. Hydrogen can only ever form one bond. Carbon has 4 valence electrons, therefore it typically forms 4 bonds. Notice how those two add up to be 8. Nitrogen has 5 valence electrons, therefore it typically forms, well, 3 bonds. Oxygen has 6 valence electrons, therefore it's very common for it to form 2 bonds. Notice that these are adding up to 8. Halogens, your chlorines, your fluorines, your bromines, and your iodines, and those typically form 1 bond because they have 7 valence electrons. Elements in the second row of the periodic table can form a maximum of 4 bonds, never more. Okay, never, ever, ever more. And then only elements in the third row or lower on the periodic table can exceed 4 bonds. So here is how the Lewis structures on the FRQs of the AP chemistry test typically show up. And that is where you should expect to see on the FRQ, you should expect to see one Lewis structure, and they'll look like what I'm about to show you. You should expect to see one shape or geometry question and one hybridization. Okay, so that's a good 3 points. And when the FRQ is about 40-something points, that's a little under 10%, and so this would be a good area that you could earn some points where other people wouldn't. Okay, so what I want to do is I want to use my general bond rules. So what I'm going to do is I'm going to use general bond properties. I'm going to not focus so much on the central element, but I'm going to say chlorine is a halogen. Halogens typically form 1 bond. And so then I need to give it 8. So that would be covering the other 3 sides pretty much. Okay. Oxygen normally forms 2 bonds. Oops. And so with that, oxygen needs 2 lone pairs. And then what I can do is I can say that that's most likely the Lewis structure. And if you actually go through and do the full process, that is the Lewis structure. Okay, so let's look at SO2Cl2. Chlorines are halogens. They typically form 1 bond. Oxygen typically forms 2 bonds with 2 lone pairs. And so this is my Lewis structure. And if you actually go through and do the process of getting the Lewis structure, that will actually minimize the formal charge. Now, this one's a little bit strange. Iodine is a halogen, but we're not really focused on the central element here. We're focused on our terminal elements. And what I do is if I go through and I do formal charge, I say, well, iodine is missing 2 electrons. This doesn't fulfill my valence count, and so what I need is I need 2 more, and I just put them on the central element. Okay, hydrogen we know always forms 1 bond but no lone pairs. Carbon is typically going to form your 4 bonds, so it already has 1 bond, so it must form it with nitrogen, and nitrogen forms 3 bonds but it needs 1 lone pair, and so this is HCN. So then we can get into some hydrocarbons, some organic chemistry here, just baby organic chemistry. We get something that looks like this. Now, this is ethanol, C2H5OH. Hydrogens are always going to be 1 bond. Carbon typically forms 4 bonds, so if I look at this first carbon, to give it another bond, that would give it 4. So then I need to look at the second carbon. It needs 4 bonds. And oxygen normally forms 2 bonds, so that looks good in terms of bonds. But remember, oxygen needs 2 lone pairs. I like to put oxygen's 2 lone pairs on the same side because it helps with polarity. But that would be the shape of or the Lewis structure for ethanol. Now, this is what it looks like on the AP chemistry test. They typically give you where they want the elements to go, and you just have to fill in the bonds. But what they'll do then is they'll say, okay, this oxygen, what is its shape? Well, what you have to do is you got to say this oxygen is bonded to two other elements, and it has two lone pairs, so its steric number is 4. So this shape will be bent, and its hybridization is sp3. Or it could say, what about the leftmost carbon? Well, that carbon is bonded to 1, 2, 3, 4 atoms, so it has a hybridization of sp3, and its shape is tetrahedral. Okay, now let's look at this. Hydrogens always form 1 bond. Carbon typically forms 4 bonds, so 1, 2, 3. And I'll figure out the 4th one later. Nitrogen typically forms 3 bonds, so what that means is that these guys are probably good. I might want to focus on this bottom oxygen. Oxygen typically forms 2 bonds, so there's another bond, and that would give carbon its 4 bonds. But we got to do lone pairs, so nitrogen needs to get up to 8 electrons, so I'll give it 1 lone pair. Oxygen needs to get up to 8 electrons, so I'll give it 2 lone pairs, and that is the Lewis structure. And so what you can do is you can pause some of these and go ahead and try them out. You should be able to go through them pretty quickly, so pause it, and I'm going to go through and give the answers here. Sulfur normally forms 2 bonds, just like oxygen, because they're in the same family. Nitrogen normally forms 3 bonds, which is perfect, because then I can get a Lewis structure that looks like that. And then we get... Okay, so let's do this last one because this one's a little bit weird. I almost did it wrong. I know hydrogen forms 1 bond, so I'm not going to really mess with the hydrogen. And carbon's going to want to form 4 bonds. So what that means is kind of if you go left to right, you'll not run into this issue. But so I give carbon its 4 bonds. Nitrogen then has 4 bonds. Okay, and this is what's actually going to happen. And so what you get, let me think about this, is you get something that looks like this, but it's a little bit strange, because what you end up getting is nitrogen that has a positive 1 formal charge, oxygen that has a -1 formal charge, but we can't do anything about it, and it's just a strange one. Okay, now last thing we'll cover in this video is minimizing formal charge. So what AP could give you is give you 2 Lewis structures here, and you got to figure out the best formal charge. So minimizing formal charge would be the best Lewis structure, but we also want to put negative charges on electronegative elements. Okay, so what I'm going to do is I'm going to go through and I'm going to slice my bonds in half, and I'm going to look at my formal charges. This would be 0, 0, 0. This would be -1, 0, and +1. So this is my best Lewis structure, the one that I've highlighted because I've minimized the formal charge. Okay. Now, on this next one, slice all my bonds in half. And I get 0, 0, 0, -1, 0, +1, +1, 0, -1. And so in yellow, maybe it's obvious this one is the best one, but I'm going to highlight in red the second best one. And the second best one would be this one that I've highlighted in red, because the negative goes on the second most electronegative element. Okay, in this last one, Carbon has a 1, 2, 3, 4, 5, 6. Whoa, -2 formal charge. Right now I say that looks kind of strange. Oxygen has a +2 formal charge and sulfur is 0. That makes sense, at least because it adds up to the neutral state of COS. This one is -1, 1, 2, 3, +2, and then 1, 2, 3, 4, 5, -1, 1, 2, 3, 4, +2, 1, 2, 3, 4, 5, +1. This one doesn't even add up. This one could be no good. It doesn't add up to be neutral. 1, 2, 3, 4, 5, -1, 1, 2, 3, 4, +2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Again, this one doesn't add up either, so I guess that is our Lewis structure. Maybe I'm doing something wrong. Give me a second to just think about this. 2, 3, 4, 5, -1, 1, 2, 3, 4. Yeah, this must be our best Lewis structure. This one is very strange. Okay, it's the only one that could add up to be our overall charge. Okay, now, that is all for right now, so make sure you're pretty good at Lewis structures and being able to do them in this sort of format where you're given the skeleton structure. Okay, good luck.